Okay, so we're gonna go over the quiz from yesterday. Okay, so this is quiz from yesterday. Let me go ahead and enlarge this up a little bit. Just a bit. Okay. All right. Can everyone see my screen?
Yes.
Okay. Yeah, go through it, and if anything, if you have any question on any one of them, please go ahead and unmute your mic and please ask, and so I can go over more details if you need.
Thank you.
You're welcome. So number one is just simple basic, and they said to measure the current. Okay, so you have to put your meters inside your circuit between your source and your first resistor. That is when your resistor in series. So that's so all the current can flow through the amp meters to get the measurement. Okay, so that's why the answer is C for 1. And number 2, that is, this symbol is represent an LED or light emitting diode. Okay, so this is a diode, and when you have this extra 2 pointy line, that means the light is blinking. Okay, so it's a LED. So the answer is B for number 2. Okay, so number 3, clowning around the laboratory can cause which of the following? Okay, you can get electric shock. Yes. You can get burns if you work at the soldering station, or you can get cut or bruises. So don't do that. Okay, so the answer is D for number 3. Okay, so everyone's good. Number 1, 2, and 3.
Yes.
Okay, next. All right, so okay, so number 4, why is it important to have permission to use the power tools for the first time? Okay, yeah, anything power tools, you have to get the instructor permission, because sometimes we need to go over and help you go through some of the safety precaution before you operate those tools. Okay, so the answer is this C for number 4. Okay, I know it's cost a lot, but it's still you have to ask the instructors to make sure they go through all the safety precaution before you operate any kind of power tools. Okay. Number 5, the safety rules should be obeyed in order to, okay, so you follow the rules, so you can finish your project quickly and in a short time possible. And also to keep student busy. Well, you know, you have to follow that procedure, so that way you know exactly what you're doing, and also to, like I said, to use the time available, you know, manage your time as much as possible so you can get things done. So, and also prevent injuries to yourself and others. So the answer is D for number 5. So all of them is applied. Okay, number 6, the term used to describe opposition to current flow is, okay, so this is from the first handout. So the answer is resistant, C for number 6. Okay, so any question number 4, 5, or 6?
I honestly did not. I thought on question 5, the choice B, keep other students busy, I didn't think really that applied. So I went with C. That was the most obvious one.
Yeah, look like more. Yeah, C is the most appropriate to prevent injury to yourself and others. That is the most appropriate, but it's also to so if you're busy working say that if you're working in the lab and you're working on lab fault, so you are being busy, so therefore you can't cause injury to other. Okay.
Okay.
So yeah, you actually, you know, you're working on your project, trying to get your lab done, and so therefore, you know, it is one of the safety rules that that you have to follow. You have to keep the student stay busy doing whatever it is, your lab, your homework, or whatever it is that's essential to complete the course.
We'll go along with that this time, Sam, but I agree with Adam. That's nonsense.
Okay, like I said,
I agree.
Thank you. Okay, yeah. Anything else, you know, can bring up with the instructors. So that's you know, like I said, C is applied to. I think C is more appropriate, but all of them apply. Okay, so next set. Okay, question 7, the unit measures of electron flow is ampere or current. So D as in ampere. Number 8, current flow in a circuit is 0.015 amp. This value can also be expressed. So it just kind of do the calculation. So I equals 0.015 amp. That's the same thing as 15 times 10 to the negative 3 amp. And we know that 10 to the negative 3 represent milli. Okay, so that's why 15 milliamps. So the answer is B as in boy for number 8. Okay, and then number 9, the ability of a quarter watt resistor to give off heat is related to its, mainly you look at the physical size. So the smaller the size, the least amount of heat it can dissipate. The bigger it is, the more heat the more heat it can dissipate. So therefore, so if you put a quarter watt resistor in your circuit and it burn out, then you probably need a bigger resistor, maybe a half a watt to compensate that.
Could we also say that resistance in a resistor is proportional to its physical size? They're sort of related.
Yeah, the physical size. Yeah, exactly. A quarter watt is very, very small. And then
Right.
half a watt is a little bit bigger. So therefore have more surface area. The more surface area, the more heat it can give off. And so therefore it won't burn up. But the smaller one, it got small little areas. So it heats up and it will burn up and then it will destroy that resistance. It will cause it to short it out.
The larger the resistor, the more resistance it generally has.
Yeah, the more heat that can give off without burning itself up.
Okay, I got that one wrong too. I went with A, but I see what you're saying.
Okay.
Yeah, a 2-watt resistor. I don't know if you ever seen it, Adam, but it's a kind of a big fat one. And basically, when these resistors get warm, that's the real test of it. So
Yes.
if you got a big one, like a 2-watt, it'll be cooler than say a quarter watt.
I see. I was just thinking that the property of resistance is what causes it to heat up in the first place. So that I went with A, but I see how they're both directly related. So I see.
Yes.
Thank you.
Sam,
Yes. Yes,
Sam.
Michael.
Now, you know the service mount resistor, the real tiny one? You know,
Yes.
what sort of voltage are those then?
I do not know. I need to look that one up. So
Okay.
I haven't worked with those too often. I usually just use a regular resistor, and that's what from the blueprint I just go with that. I
Right.
haven't worked with very tiny surface mount yet.
Yeah, I know the through hole one usually, you know, like you said, the quarter, half watt and 1 watt, they go up in size.
Yes.
And I just wonder with the surface mount, does that rule still apply?
Yeah, they're supposed to be the same,
It still go up in size?
right? They have to be the same depending on how that resistor can handle the power.
Okay, so therefore all these micro size surface mount usually is quarter watt or maybe even less than, I presume.
Yeah, you're looking at approximately, and it's in very low side because they're going to have to handle very, very low current in like in the milliamp and microamp.
Okay,
So therefore that, yeah, the heat that dissipate from it is it's very, very small on it. So yeah, those surface mount would definitely able to withstand it.
okay, all right, thank you.
You're welcome. Okay, any question number 7, 8, or 9? Okay, next set. Okay, so this is come from this is directly from the lab vote number 10. So therefore, so if you did this one, so the answer should be like 68 ohms at plus or minus 20%. And you can look at the color band. So blue is 6, gray is 8, black is 0, and it's got no band in the fourth, so none, which is represent plus or minus 20%. So therefore, you just put 68 ohm times 10 to the 0. So 10 to 0 would be 1. So 1 times 68 would be 68 ohm plus or minus 20%. Okay. So the answer is B as in boy for number 10. Number 11 is the property of conductance is ease of current flow. So the answer is D as in David for number 11. Okay, so number 12, okay, the total voltage in the circuit shown is, okay, so you got so this is going to a 1.5, 1.5, and 1.5. So therefore this one be 4.5, and then this one is reversed the other way. So therefore you have to subtract 1.5 from it. So therefore leave you a 3, and 3 minus the 1.5 leave you just with 1.5. So the answer is A here, okay? So you can, like I said, if you have some time, you know, you can also run a simulation on PSpice, not PSpice, on MSIM. You would see it, you know, here I did a run across that, run it, and it shows either 1.5 or depending on how you place your meter, it can be read now 1.5 or negative 1.5. Okay, like Mr. Pham said, you know, most of the time as you as a lab technician, you're gonna be using your meter just to measure to get the value. Okay, so make sure once Mr. Pham goes over a little bit more on the MSIM, and you can use that to do this kind of simulation to collect your data. Okay.
Sam, I had a quick question about this one.
Yes.
Just from a practical standpoint, my understanding is that when you connect battery cells in series, you're increasing your circuit voltage.
Yes.
Whereas if you connect them in parallel, you're increasing your amperage.
Your current. Yes.
In this case,
Mm-hmm.
if you have 1.5 volt battery to start with,
Okay.
why would you connect 5 of them in series only to end up with 1.5 volts at the end anyway? Wouldn't you
Okay.
just use one battery for 1.5 volts if that
Yeah,
was?
yeah. This one is just to test your understanding, because you got
Okay,
this
right.
is 1.5, and then this one. So you got this one is a negative to a positive, so that's a positive 1.5, and then this one's a negative to a positive. So a positive added to a negative, so therefore that's going to end up adding together, and this one's going to be adding together. Now this one's going to be a positive to a positive, so therefore they're going to repel each other. So
Right.
therefore it's going to decrease by 1.5.
Right. So
And
that's just
then-
an academic example, so purely theoretical.
Exactly. So
You
therefore,
wouldn't
yeah,
see that in a circuit anyway.
yeah, so it reverses itself. So this one is and this one cancel out this one, and this one would end up canceling out this one, so leaving you just with this one
Right.
It's a
available.
test of observation.
Right,
Yes,
exactly.
there you go. Yes, you have to look at the you look at the symbol here, and what you have to define how you interpret that. Okay,
Exactly. Okay, thank you.
you're welcome. Okay, any question number 10, 11, or 12? Okay, no question. Next set. Okay, so number 13, this one is coming directly from the Ohm's law. Okay, so voltage, how they're related to each other. So this is directly proportional. If you decrease the voltage, you have to decrease the current. If you decrease the current, you would decrease the voltage, or you increase the current, then you would have an increase in your voltage. That's what you call directly proportional. So the answer is D as in David for number 13. Okay, number 14, when you use any form of Ohm's law, how many value must be known? Okay, so if you want to solve for voltage here, you have to have either I or R. Okay, so therefore at least two variable you have to know the value for in order to solve for the third one. Okay, so the answer is B as in Bob for number 14. Okay, number 15, if an electric circuit has a current of 15.5 milliamps and a source voltage of 20 volt, the total resistance is, okay, so this is just apply Ohm's law. Okay, so current is 15.4 milliamps. So I converted to the basic, basic unit. That's come to about 0.0154 amp. And my voltage is 20 volt. Okay, and then a resistance equal voltage divided by current. Okay, if you put that and then do your calculation, should come up to about 1298.7 ohms, and you can round it off to 13. That's good enough. So the answer is A as in apple for number 15. Okay, any question number 12, 13, 14, or 15? Okay, sound like everyone's good. Okay. Next set. Okay, so this one number 16. So this is Ohm's law. Okay, so you can use Ohm's law. You can use it to solve for voltage. You can use it to solve for current, or you can solve for resistance. So the answer is D as in David for number 16. Okay. Number 17, electric circuit where the voltage is 100 volt and the resistance is 25 kilo ohm. The current is, okay, so apply that. So we're going to have to solve for the current. So we know the voltage is 100, resistance is 25K. Okay, so therefore it's going to be 100 volt divided by 25K. That's what give you 4 milliamps. So the answer is A as in apple for number 17. Okay. Now number 18, when you connect a voltmeter to read a DC voltage, okay, the voltmeter is connected across the component, as you can see on the in this here. Okay. Oops. Okay, so you can put across or in parallel with the component. You can do this one here, the R2, or you can do at R1 would be the positive side here and the negative side here. And same thing with R3, you got a positive side here and the negative side here. So it's always going to be in just across the component. Okay, so the answer is C as in Charlie for number 8. Any question number 16, 17, or 18? Okay, everybody's clear? All right, next set, page down. Okay, so this is coming to style. We're looking at the Zener diode and what is V out. Okay, so in order to find out what's going on with your V out, first thing you in this case you have to first thing ignore the Zener diode and just calculate what V out is. So V out, we're going to apply the voltage divider. So therefore you take the E times R2 divided by the total resistance. So total resistance is the quantity R1 plus R2. Okay. And then once you do that calculation, you find out the V out is 10 volt. So the answer is B as in Bob for number 19. And then 20, now that we have the Zener diode in the circuit, what would happen to, what would be the V out, okay? Since the Zener diode is only 5 volts, so, and then the V out was saying 10 volt, therefore in this case, it will go into breakdown, and at the breakdown, the V out would take the value of your VZ, your diode, your Zener diode voltage, okay? In this case, it's only 5 volt. So V out end up with 5. So the answer is A for Apple for number 20. So any question on 19 or 20?
Yeah, I have question for 20.
Okay.
Right. This volt coming VZ 5 volt, right?
Yeah, 5 volt. That is determined by this. So when you buy the Zener diode, you buy a 5 volt Zener diode. So this is controlling the whole voltage that's going to go out when if any kind of voltage here at point A, if it's exceed this amount, the V out is only taken in this amount. It just cut off whatever it was, like 10 here, and then it's going to cut off that 10, and then they're going to give you only 5 maximum.
Okay, I want to say also this 5 plus 10 equal to 15, the main source, right?
No, this one it just they just want to test you, do you understand the concept of when the Zener breakdown, okay?
Okay.
When the Zener so it said that you control the voltage. You don't want it to be anymore. You just wanted a 5 volt possible outcome. Okay. So that's why you protect your circuit by having a Zener diode here. So that way you don't get any more voltage here that can burn this resistor here. Okay. So if you put a 5 volt, that would be safe because then you got a small current that would be traveling through here, and you're gonna be this resistor would able to survive.
Okay, thank you. Thank you,
You're
clear.
welcome.
Thank you.
Okay,
Okay.
on this problem here, you must be understand the Zener diode. If they break down, that means output across this Zener will be only 5 volt. If you get a more than 5 volt, they break it up. Try to keep the constant voltage. Okay.
Yes.
So normally in the Zener diode, you don't have a question number 19. They just asking about what the V out. So in order to know what the V out, then the first thing you have to do is make sure with down the Zener, then what the voltage supposed to be at the output. For example, in this case, it's 10 volt. Now, 10 volt will be higher than 5 volt of the Zener. So that's why they break it out. Okay? The thing is from later on, we're not asking you to calculate the width down the Zener, but you must know before you decide a Zener will be breakdown or not, or working normal. You must be get the voltage at the output without the Zener in order to tell they break down or they not, or they just working normal. Okay.
Okay.
All right. Thank you. Okay, back to you, Mr. Pham.
Okay. Thank you, Sam.
You're welcome. Thank you.
Mr. Pham, I don't know if you want to answer the question. Early on, you asked if we had a question, but I need to share the screen.
Okay. What you go ahead and say, I see what.
Okay. All right, let me see. Oh, yes. Share screen. It was about this one right here. So on the Excel, this is the multi-sim 7, but so we take the voltages across the resistors, correct?
Correct.
All right, and then let me stop share and go back to this one. Wait a minute, hold on. And then so this one here, you wanted something like this, correct? And then we should get, why is this thing not doing it right? I don't know why this is. Oh, okay, there we go. Okay, so that's the waveform you wanted, correct? Can you see that, Mr. Pham?
Yeah.
Okay, so the measurement would be taken between the valley of the red one, the red waveform, and the orange waveform, the distance between it, like the delta. Is that right?
Now, the orange, that's the input, right?
Right.
And the red, it is the output.
Okay, so you only wanted the measurement of the output?
Exactly.
Okay, thank you. Let me unshare. There we go.
Okay, thank you. Okay, now make sure you understand on the quiz. The quiz just given to you very, very basic in electronics. When you're doing the quiz, you can answer right away without any looking back to the notebook, the handout, whatever. Then you will be okay. Otherwise, you're not up to the point we wanted. After you're done, in the program you apply for the technician, you get an interview. And you have to review what you've been learning so far. You cannot go to every document, too many things. So that's why using the quiz, go over and over. That will be helping you. Okay. On the quiz, I just given the basic thing you must know without any information from somewhere else, then be okay to me.
Hey, Professor, should we memorize the resistor color codes
Now,
too, or is that something we should be able to just go to the chart and refer to?
now go to the chart. Normally, interview, they're not asking you that kind of the question. If they do, then you have to let them know. I know how to do it, but I need the chart. That's it. However, if you want to know the value of the resistance, easy way. Let me get the DMM. I can measure, I can tell you exactly the value. That means that you are a technician, you know what to do, how to do it. But I never seen in the test from the company, they asking for the value of the resistor using the color code. Okay, anything else? The quiz will be helping you to review when you get the interview for the technician. Okay. Yeah. Any question? Go ahead. Okay, if it's not, okay, I go back. Quick review for what we done so far on the transistor. Okay, from yesterday, we already know you get the transistor. Okay, when you see the transistor, you're supposed to know everything. First thing is, this is the base. This is the collector and admitter. Okay. So that is VBB. So in order to get the current or the voltage like VB, VC, VE, or IB, IC, IE, what needs to be changing in this circuitry? For example, you want IE equal 1 milliamp. Then what can we do? We're supposed to get a VCC, VBB. Same thing. That will be related into the designer. When they design the circuitry, they have to get what they want. They want the IA, how many milliamp, or IB, or NIC, or they want VB, or VC, or VE. What do you think they should be changed in this circuitry to get the one they wanted? Change what?
IB.
Then which one will be changing on this circuit? You want the current you want it, or you want the voltage VB, VC, VE you like to be. What you're supposed to change in this circuitry?
RB,
Yeah, you can change RB or RC or RE, correct?
right?
In order to get the current you want or the voltage you want. That is normally happen for designer. However, at this time, very simple to have the designer to do it. That means you can run MSIM7 or the PSPI simulation, and you can change the value of RE or RB or RC until you can get the current you wanted or the voltage you want. Only thing what to do, change the value RE, RB, RE. And now easy to designer to do. They just go to the simulation and they try to changing the value of RE, RB, RC. Then they can get the current they wanted or the voltage they wanted.
So, Mr. Pham, is this something that, say you could take this circuit and, well, you could play around with it on Multisim 7 or PSpice or something like that?
Yeah, that exactly.
Which one would be better, Multisim 7?
No, either one can be the same. The reason we're using MSIM7 first, the thing I want, students try to get along with the drill lab they must be doing. The thing is when you simulate MSIM7, that teach you how you're using the meter to measure, oscilloscope to measure, okay? And apply the generator, for example. More flow with what you really doing in the real work. Be more theory, okay? Not help you to understand. However, it's not helping you to using real equipment. They're doing the same job. Okay? And when you're looking into the circuitry, you need to know is it a NPN or PNP. Okay? And for NPN, how the current IB, IC, IE will be flowing. IB coming in, IC coming in, IE will be leaving. Okay? And the formula where IE will be equal IB plus IC. Also, you can get another formula for calculate the beta. Okay? Beta equal IC over IB. Okay, what is the beta? Just tell me the definition.
Current gain.
Again, yeah.
You have to say DC current gain, right? If beta equal 100, you get a 1 milliampere IB. Then you have to multiply 100, then you get the current IC will be 100 times bigger. That's what they call a current gain. Okay? And now, if I want to measure VB, I set VB. What that means by basic definition for VB. The thing is when you measure the voltage, they must asking for the high and the low side. If I say I want VB, and I given you the meter DMF, you must be know how to connect the high side of the meter and the low side. So by definition, VB will be equal what? They will be measured. Measure what? From where to where?
Voltage from base to ground.
Exactly. From base to ground. Common. You understand it when they're talking about measure the voltage. If they want only single point, they must be measured with respect to the route. Same thing. VBVC will be measured from the collector to route. Same thing for VE. Will be measured from the base, from the meter to the route. Okay, if you get any question, just let me know. If I want RB, when the definition for RB means the resistance from where to where? RB, base resistance, will be measured from where to where?
BB at base.
Base resistance. Okay, from base to the route. That is the base resistance. Okay, if you want to measure the V C, VRC, that means the voltage across RC. Okay, that means the voltage across. And if you want to calculate the VRC, they will be equal IC times RC. That means that this is a completely definition. And you must understand for later on. Okay?
Okay.
And we already know that thing we already done. Okay? You only thing is make sure you understand on this one when you're looking into a transistor, you know, NP, 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 and how the current flowing. Okay? And basically, in the transistor, you get a two diode, one diode from the base to emitter, and one diode from the base to the collector. Okay? They're using two diodes to make a transistor. And that's why you can get NPN or PNP. Okay?
Mr. Fan,
Yeah.
can you go back? Well, even this one's fine. Well, right here. No. Go back to the DMM.
This one?
No, go down. Right here. Okay. When you test it with a DMM, when it's forward bias, you get a voltage drop of 0.7. When it's in reverse bias, shouldn't that read 0 instead of 2.6?
That's what they from the textbook. You
Right.
can try.
But if it's just a simple diode, then there should be no voltage drop. Isn't that correct?
Okay, now, if you're looking into that one here, they connect positive to the emitter, right?
Right.
And the negative to the base. So basically, they will be reverted.
Right.
Okay, they reverted. I'm not for sure, you know, what they supposed to get.
I think it should be 0 because when there's a
That
diode,
cannot be 0.
it cannot be 0.
Yeah. But what I telling you, if you want to try, then you can do it in the lab, easy to recognize. Is it the textbook correct or not?
Okay.
However, easy way to do. When you connect for this one here, that means you connect from B and E. That means you get the first diode. And basically just measure the resistance. Okay? That's a forward bias. So the resistance will be reading maybe 1 kilo ohm, for example. And then you revert that one. And the value reading supposed to be 100K or higher. That means good diode. You measure one will be forward bias, the resistance will be very small. And you revert it, that will be open circuitry. The resistor will be higher. At least have to be 100 times higher than the diode. It's good. That's what normally we use it. Okay? And that means you test first diode and now you can test for BC, second diode, same way. Okay?
So Mr. Pham, so when we go to the lab, we could just ask for a transistor and practice and see if we can get the readings that you got on the screen. Is that correct?
Yeah, you can, you don't turn on, you don't connect power. And now you can see the transistor, you can try.
Yeah, you just do this with the multimeter and the transistor.
Exactly, they show here.
Okay.
And let me know, is it working okay? Or correct like the way the textbook do it or not?
All right.
Okay. This one done, this one done. Now we're talking about this thing before we go more. So basically, the transistor, they can be working in the three operation. They can be cut off, they can be active, or they can be saturation. Okay. The purpose, if they cut off, they're using that for the switching. That means like, on and off. Okay. And they can be inactive. That for amplification. If you want to design the transistor for the amplify, what they amplify? They amplify your voice, make your voice louder. Then they have to be inactive. Okay. And the last one, saturation. Saturation, the same like cut off. They just use like the switching. That means whoever on Tech 2, you're learning about the gate, OR gate, AND gate, NAND gate, inverter. If you're looking inside, they just a transistor. However, that transistor only working in saturation. The thing is on the logic, they just want 0 and 1, 0 volt, 5 volt. You don't want amplifier. Okay, so they cannot be in active region. And finally, breakdown. That means they will be destroy the transistor. Okay, few things here I given to you. Cut off then diode from the base to the emitter be off. That means the voltage from the base to the emitter cannot higher than 0.7 volt for silicon. Then the diode will be open. And that diode will be open, that means like cut off. So the current IB, IC, IE equal 0. No current flowing. Okay. In the active, diode from base to the emitter must be on. Okay. And the diode from base to the collector, basically they will be on off, reverse bias. Last one for saturation. Both diodes will be on. And the VCE for saturation almost 0. That's what you must understand that. Okay, now we go back here. This is the graph for IC. First VCE. Okay, that's talking about the load line. If you're looking on that one, you understand this stands for what? What stands for?
Is that base current?
The base current. Okay, that will be IB.
Hey, Mr. Pham, most of the time, IB, it's mostly in microamps, right?
Yeah, normally they're very small. Okay, that is stand for IB. Now, if I'm looking here, I say IB equal 20 microamp, 40, 60, 80, 100 microamp. Okay, and this stand for what?
BCE?
Right here,
BC, yeah.
BCE. And that one here stand for what?
I see.
I see.
IC. Okay, and now if you're looking into here, you can see they get the 3 regions. First thing, the region right here. What is the region right here?
Cut off.
Right here, right?
Yep.
Cut off. What the region in this area here?
Saturation.
Active.
Right here,
Oh, that's saturation.
saturation. And anything in here will be.
Active.
Active.
Yeah, now you guys can understand better than myself. When I started, I looking into, I not quite understand. Maybe the instructor don't know how to teach.
Hey, Mr. Pham, so the active is between saturation and cutoff.
Yeah. This active. Cut off here. Saturation. Now, why do we need this wrap in here? The reason is the designer, when they design transistor circuitry, they have to know what the current, okay, supposed to be. If you get IC, IB, then you know IC, IE. So that's why normally they have to using what they call a DC load line. Okay, I given you the example. They draw the line here. Okay, they draw the line here. So I can telling you at this point what I be equal.
60 microamp.
You go here, right?
Yep.
50 micro.
60
And,
mic.
and if you want the IC, you go this way, right?
Right.
You can get the IC here. You want VCE, you going down here. Then you get the VCE. So this line they call a DC load line. They can pick any point in here they want it in order to get the IB, IC, and VCE.
Hey, Mr. Pham, just one more time. The long line where you got going from 14 to approximately 14, 16, how did you determine that line? One more time.
No, we're not talking about how to draw the line. Right now, I'm talking about you want to get the point in the circuitry, you need to draw the line. But I'm not telling you how to draw it.
Oh, okay.
Okay. When you draw the line, you can get this point right here. Normally, they call a Q point. At that point, you know what IB, IC, VCE. Okay? Basically, when you design your amplifier, you don't want to pick the Q right here. Why?
Too close of saturation.
Very close to the saturation. So when the transistor heat it up, Q point can a little move it. And if they moving in this area here, they're telling you they no longer amplifier. Or you don't want to pick the Q point right here, very close to the cutoff. If they go to the cutoff region, they no longer to be amplifier. So that's why they really want any Q point in the middle in this area. Okay?
And that's the active area.
Right. You want to design amplifier. You don't want to be saturated. You don't want to be cut off. That Q point supposed to be in the middle. When the temperature raises, Q can be moving a little up, little down. No big deal. They still in active region. Okay, you understand the purpose for the DC load line that apply for engineering when they want to design the circuit with a transistor. And now I will tell you how do we draw. Okay, now if you get that one, the circuit here, transistor right here. Okay, if I get the VC, okay, equal 10 volt. And also, you can get the IE, IC, IB. So First thing you need to draw the line, you need to point. Okay. You need 2 points to draw that line. First thing I say, I want the point here. So what the VCE equal?
10 volt.
So you pick it 10. And then you need to pick up a 1 point on the here. I don't know which one. Pick this one. On this point here, what VCE equal?
0.
Exactly. VCE equal 0. That only telling you the current IC will be okay. IC will be equal VCC divide RC. Okay. That means and you can get that value when they given you the whole circuitry. And that's why you can get a 2 point here, point A and point B. And you draw one line from here to here. That's what you get any Q point you want. Okay. So in order to draw the Q point, finally, I can give it to you. Okay. VCE will be equal VCC and IE. Okay, VCE equal VCC. Make sure IC equal 0. IE, you can get the value with VCC divide RC. Make sure you know VCE equal 0. So in order to get 2 points, 1 point you set IC equal 0 to get the value of VCE. And another point on the current IC, you set the VCE equal 0. That's what you can come up with what the value of IE equal. And you draw the line. Okay, basically for the technician, only thing make sure you know how do we need the graph for the DC load line. That's what we're talking about, DC load line. You get the Q point. The thing is we not design anything. However, at least you must be understand. If they say, I get the point at this point right here, can you tell me what IB equal, what IC equal, what the VCE equal? Then you must know how to identify that. Okay, any question on the DC load line? And you make sure you understand for engineering, when they design, they don't want the Q point in here very close to the cutoff, or any point close up here, very close to the saturation. Okay. The thing is, when you want Q point, you want they be inactive. Okay, they don't want it to be saturated or cut off. Okay, next one. Now, this is they given you little more detail. How to draw the load line. Okay. If you want more, you can read this one. They say point A right here. At saturation, I saturate equal VCC divided to RC. Okay. So this is your circuitry right here. VCC is 10 volt, divide 1K, that given you 10 milliamp. So you can pick a 10 milliamp right this point right here, 10 milliamp. And now you need a point B. Point B at the cutoff, VCE equal VCC, 10 volt. Then you can draw the line. That is very clear. How to draw the DC load line. Okay, any question on that? Enough now. That will be talking about mode operation. Cut off. That means you get a 0 volt right here at the base. Transistor will be cut off. That means this diode here, reverse bias, not on. They will be off. So now look like they just like the switching between collector and the ammeter. Open, no current flow. Saturation. Okay, saturation, that means when you get a higher IB, they can go to the saturation. And this current IC here will be IC saturate. They using like the closed switch. That means they allow the current flow here. And the voltage VCE almost 0. Okay, so they combine cutoff and saturation to make like the switching. This is the open, this is the close. Okay, right here. You see that? They close. So now you understand. Cut off and saturated using for switching, especially in the digital circuitry. Then they're using the transistor to build the logic gate. You can get the AND gate, OR gate, inverter, okay, NAND gate, NOR gate, whatever. If you're looking inside that I see, they just the transistor. However, that transistor must be working in saturation. You don't want to amplify. On the logic, you can get either 1 or 0, 1 volt or 5 volt. You don't want to amplify anything. So the transistor to build the logic circuitry, they must design to working in saturation.
Teacher, I have a question.
Yeah,
Okay, and on saturation, to get the IC of saturation, we have to make a RC smaller.
no, that depends. Okay, when you design the circuit in saturation, then you have to know what IB, what IC saturate supposed to be. In order to know, you go back to here. Okay, if you pick up the value of IC right here, they will be insaturated. Okay,
Okay.
okay, now on this example, if I given you the circuitry here, I want to calculate the IB, IC, IE, VE, VB, VC, or VCE. You're able to do it right away for me. I given you only one, IB. IB, you want to calculate it, you take VBB minus VBE divide to RB. Okay. And on this one here, you can see you can get it done for me in about 10 minutes. I already given you this formula. Okay. You know IB, you know IC, you know IE. And you can telling me what VE equal VB, okay, and VC or VCE. Do it for me. So I have to be active in the lecture. That means you have to do it and let me know what you get. Not I just look into that without doing anything. You never can get what you wanted to learn. Okay, go ahead and telling me who can done quickly. So we can get the answer for the student. They can review later on. This is a very basic, so that's why I want you to do. More complicated, we don't care. The harder part will be calculated IB. I already given you the formula. Substitute the value telling me what IB equal.
43,
Milliamp. What you get?
43 microamp.
40 joule.
43,
43.
43 microamps.
I want milliamp.
Okay, well, if you want milli, then it's 0.043 milli. Just move the decimal point 3 places.
0.043.
0.43.
0.43, right?
No, 0.043. Because if you move the decimal point to the right, that would be micro. Move it to the left, that's milli.
That is, the other student get the same answer.
That's IB.
And I see.
IC is 4.3 milli.
Exactly. .3. I don't put a unit. They already telling you in
Yeah,
milliamp.
Yeah.
IE.
What is that, 1 plus beta? IE can be IC plus IB.
We don't want that formula.
You don't want that one?
I want using the formula.
Or you want the 1 plus beta
Right.
something?
1 plus beta.
4.343.
IB. What you get?
4.34.
Okay, one answer will be 4.34. Who can verify correct or not? 4.34. Okay, that means IB equals 0.043 times 101. VE.
Hey, Professor, since there's two formulas for IE, how do you know which one to use?
That's what I
In which
already
situation?
told you guys. You can get IE, IB, blood, IC. We don't want to use in this formula. Okay? The thing is, IB is too small. So cannot get the value we want. So instead using this formula, you using this formula for me.
Okay, I got it. Thanks.
Welcome. VA,
0.
So
VB,
4.3?
come on.
No. Wait a minute.
0.7?
4.7.
5,
0.7. Oh, from base to ground. That's right,
5,
base to ground.
VC,
BC is
7.7.
you want to calculate the VC. I
If-
give you the formula.
VC would be VCC minus
VCC
ICRC.
minus
ICRC.
RC. You already know IC. Now VCC. Telling me what VC equal. Who get answer for VC?
7.7, anybody get that?
Yeah, 7.7.
Yeah, I got that.
Okay, 7.7.
7.7.
VCA. Remember, VCA equal VC minus VE. VE 0. VCA equal.
7.7.
7.7.
That's what I want. When you look into the circuitry, you can do calculation without anything else. Try to get up to that point.
Next.
Perfect. Any question on that? Any confusing, any not clear? Bring it up. Okay, on this circuitry here, they already given to you the answer. Okay, so I don't have to do anything. You have to do by yourself. That's what circuitry they call admitter bias. And already get the answer. Now, another way to get the DC voltage in general, they're talking about DC bias. What that mean? That means we need the power DC to make the transistor working. On this connection here, okay, they call a admitter feedback bias. So they connect the RB here. So basically, you can see the current flowing here, going down here. Okay. In order to solving what IB equal IC, IE, and VCE. You can run the simulation, you can get the answer quickly. However, they say better than the Bay bias. That means better than what we do in calculate here for the Bay bias. Okay. However, kill points will be moved and they're not popular. That means they're not easy. Okay, I just try to give it to you a different type of the bias. Next one, Bay bias. Look like almost the same like this one. However, they don't have an admitter resistance. The least predictable kill point move with replacement, kill point move with the temperature, and this circuitry will be not practical. That means you cannot see in the circuitry they design by this configuration. Okay, that's not practical. Collector feedback. So you can see you can get the IC going here. Okay, IC going here, right? IRC going this way. When they get to this point, one will be going this IB. One will be go inside IC. Okay. That's what they score better than admitter feedback bias. However, they don't know, they don't want Q point to be moving. And that will be a very limited application.
Hey, Mr. Pham, show which way the current is flowing.
The current flow this way. This the current right here. They're not IC. I. When they reach to this point right here, one go this way. IB. One going down here. IC. This is the collector. Okay. That's how that current flowing.
So the IB goes through the resistor?
Yeah, go to the base.
I thought one was a NPN, it go the other way.
Yeah, and PNP, that's a NPN. PNP, that's different. They
So-
now try to show you for both, only one.
So IB and IC will eventually meet up and become IE.
Exactly, same thing.
For feedback.
But don't confuse the current flow here. Not IC. IC will be the current flowing from the collector to the transistor.
So you said IC is after that current goes through the resistor, then it becomes IC.
Exactly. When they go from collector to the transistor.
It's weird.
The thing is the current flow at this point go across IC here is not IC in this case. IC will be going collector to here. Okay,
All right.
so that will be limited application.
Hey, Mr. Pham, just one last thing. On that I, is IC and I the same magnitude, the same amount, the value?
Now, the thing is they go divide, one go to IB, one to go to IC. They're not identical.
Oh, okay. So in other words, the I could be say like 5 milliamps, and then a small amount would go through IB and the rest would go through IC.
Exactly.
And okay, so, all right.
Yeah, Joe, I think if you look at it as a parallel circuit, that's what it is. The current gets split up.
Okay, yeah, thanks, Mike.
Okay, on that one, they're using two power supply. Normally, they not design that. Why? Need more power supply. One positive, one negative. Okay, that's what they call a dual supply at meter buyer.
Hmm.
That is stable, working good. However, require dual power supply. They don't want that. We can use one power supply, still make it working.
More expensive.
When you have to get two power supply, not more money. But when you're looking into the circuitry, you're able to recognize, okay, on this circuitry here, they're using two power supply, one positive and one negative, okay? And that's what not application. This is the showing you how to calculate the current IE for two power supply. So IE, we already given to you, VEE minus 0.7 divide RE. Remember, the voltage here, VEE. That will be negative.
And assume the zero in the base.
Okay. Now, if you do calculation, you understand that diode here, plus minus 0.7. So you can draw the loop this way. Go here. This is a 0. Okay. So this will be a plus 0.7 and minus VEE.
Hey, Mr. Pham, can you write it out?
Okay, so if you draw this loop, you can see first thing plus 0.7. This is the current IE. Plus IE time RE, that RE.
Right.
And minus
Minus 2.
VBB EE.
Okay.
Everything equal.
0. Okay. There we go.
So you want IE, then you can say IE time RE. Bring to the other side. VE will be positive. 0.7 will be negative. So that's why you can calculate the IE equal VEE minus 0.7 divide. That's what I given you right here.
And Mr. Pham, in this loop, what happened to the 2.7K? Because the bottom of it goes to ground. Isn't that part of the loop?
This is round, nothing.
I'm the 2.7. Isn't that part of the loop?
Yeah, they going from here.
So where's that at in the equation?
They zero.
Okay. So it would be okay to put in the equation 0 times 2.7, and then that would make that 0, and that's why you didn't put it in there. Is that correct?
Right. Okay. This is a very important for you. We try to finish that one for today. That one, first thing, they using only one power supply. You see that? Only one power supply. However, they adding two resistor R1, R2. If you get the VCC and you get to R1, R2, you can get the VBB by voltage divider law. That means VBB equal right here, R2 times VCC divide R1 plus R2. So basically, they adding two more resistor. They don't have to using another power supply. That must be cheaper. Resistor cost 5 cents. Okay. However, power supply cost more money. So this is a configuration we'll be using on the time. Okay. Now, in order to get the V voltage VB right here, then you must be using voltage divider law. After you get the VBB, you want VE. The difference between VBB and VE, 0.7 volt here. Okay, so VE equal VBB minus 0.7. Then you get VE. And after you get VE, you can easy to calculate the IE. IE equal VE divided RE right here. Okay. And after you get the IE, you're able to get IB by the formula we already given to you. Okay. And after you get IB, you can easy to get IC. IC equal beta times IB. If you want VRC right here, across RC, IC times RC. If you want the voltage VC collector here, and you know, will be equal VCC minus ICRC. Make sure you look over and guarantee everyone must know how to do this calculation. Interview they will be asking you. And that normally in the electronics, when we're talking about the transistor, this configuration will be used.
That's the one you give on the test, right?
Right. I think they get the example here, okay? But you try it by yourself. Next meeting we will go through that. However, what I want to emphasize to you, this is the one we're using on the top. And if you're looking into the circuit board design, most of the circuit will be using voltage divider. That save money. They need only power supply. And they can do it easy, cheaper. Okay? Any question up to this point?
Hey, Mr. Pham, can you scroll to the top of your handout for a second?
The top or
Yes,
what?
the top, yes, the very top. Very top. Yeah, I just wanted to look at that, make sure I got that one. Okay, thank you.
You're welcome. So any question up to this point? I hope you guys can understand a little more. What I mean, I want you to say a very any question regarding into the transistor and any very simple calculation, you're able to do it quickly. That's what I want. Normally, you can see, just learn one time, they not really understand. However, second time, you get much better. And you can say, how come Mr. Smith keep asking questions? He been with me too long. Okay, so tomorrow you guys will be in the lab.
Okay, thank you.
Yeah,
Thank you.
so we'll see you guys next week.
Thank you, Mr. Pham.
All
Yeah,
right, now.
bye now.
See ya. Bye-bye.
Bye-bye.
you.
Good
Third,
night.
bye.
Thank you.
Thank you. Good night.
Good night.
Good night.